Welcome to Physics Uncomplicated. Today's chapter, Units and Measurements, marks the beginning of our animated lesson series for Class 11 Physics. So sit back, relax, and enjoy as you learn the key concepts of physics. Each chapter in this series is intentionally kept to a maximum of 12 minutes to convey only the essential facts and ideas for that particular topic. You may use these videos as a supplementary aid to refresh your understanding of the chapter. Wishing you all the best.
Before we start our chapter, let's take a moment to introduce the characters who will appear throughout this animated series in both the Class 11 and 12 videos.
Welcome, students. Let's begin our chapter for today, Units and Measurements. The fascinating world of physics starts with measurements, and to measure something correctly, we need to use an appropriate unit. Let's clarify this with an example. Imagine it is prehistoric times, and a caveman wants to install a window in his cave. However, he does not yet understand the concepts of units and measurements. Without proper measurements, the hole in the cave could end up being too large or too small for the window to fit, resulting in a very frustrated caveman. In ancient Europe, people measured using their body parts, such as arms and legs. Even today, we still use these references like cubit, yard, and feet. Until a few decades ago, people in India used a traditional form of weight called seer, which is roughly equal to today's 1.25 kilograms. As trade between countries increased, inconsistencies between the regions arose. This highlighted the need to standardize units of measurement to eliminate confusion. In the early days of science and engineering, different regions and disciplines used their own systems of measurement, which led to confusion and inconsistency. Three such systems were widely used. CGS, centimeter gram second system, was popular in theoretical physics. It used the centimeter for length, gram for mass, and second for time. It worked well for small-scale measurements, but became cumbersome in larger applications like engineering. FPS, foot-pound-second system, used mostly in English-speaking countries, relied on the foot, pound, and second. While practical for daily use, it wasn't ideal for scientific work due to its non-decimal nature and inconsistent units. MKS, meter kilogram second system, emerged as a more practical alternative, especially in engineering and mechanics, offering larger base units and aligning more naturally with real-world scales. To unify science and technology globally, there was a clear need for a single coherent and decimal-based system. This led to the development of the SI units. SI units are classified into two main types: fundamental units and derived units. We also have a third type called supplementary units, which act as supplements to the fundamental units. The fundamental units are meter, kilogram, second, ampere, Kelvin, mole, and candela. The supplementary units are radian and steradian. Any other unit derived from fundamental and supplementary units are called derived units. 1 meter is defined as the distance light travels in vacuum in 3.3 into 10 to the power of minus 9 seconds. 1 kilogram is the mass of a specific platinum iridium cylinder kept in France. However, in 2019, the world adopted a new definition of the kilogram. In simple terms, 1 kilogram is the difference of mass between 1.4 duodecillion cesium atoms in the ground state and the same number in the excited hyperfine state. By the way, duodecillion means 10 to the power of 40. One second is the time it takes for cesium 133 atom to vibrate 9,192,631,770 times. Let's look at the definitions of some of the other units. 1 ampere is the electric current when 1 coulomb of charge flows per second. 1 Kelvin is a unit of temperature on the scale starting from negative 273.15 degrees Celsius. 1 mole is the amount of substance that contains 6.022 into 10 to the power of 23 particles. 1 candela is the brightness of a light source in a given direction, like 1 regular candle. In supplementary units, a plane angle is the angle between two lines that meet at a point measured in radians. A solid angle is the three-dimensional angle formed by three-dimensional space around a point measured in steradians. By combining the fundamental and supplementary units, we get the derived units, like force, whose unit is Newton, which can be expressed in kilograms times meters per second squared. Now that we have understood the concept of units, let's understand some of the principles of measurement. For that, we need to understand the difference between accuracy and precision. Imagine M is an archer and is aiming at the target. Accuracy is how close the arrows are to the target's bullseye, and precision is how closely the arrows land to each other, regardless of whether they're near the bullseye. There is a possibility of introducing errors during measurement, which can be broadly classified into two categories: systematic errors and random errors. Systematic errors are consistent mistakes that skew all measurements in the same direction. For example, if a ruler is bent, every measurement taken with that ruler will consistently produce an error. On the other hand, random errors are unpredictable and vary from one measurement to another. These errors can occur due to environmental factors such as fluctuations in power supply when using an instrument. Significant figures are the digits in a number that indicate the precision of a measurement. For example, if a certain measurement reads 23.9, then the measurement has three significant figures: 2, 3, and 9. Here's a very simple explanation of the rules of significant figures. All non-zero digits are always significant. Zeros between digits are significant. Leading zeros before digits are not significant. Trailing zeros after digits are significant only if there's a decimal point. Dimensional analysis is a method in physics to check formulas and convert units by comparing the basic types of quantities like length, mass, and time. In simple terms, we check if LHS is equal to RHS. Thank you for participating in this class. I hope you enjoyed the video. I'll see you in the next class where we will discuss motion in one dimension. Until then, goodbye.